Hi all, my name is Mark Beliaev, and I am a graduate student from the University of California, Santa Barbara. Today, I will go over our work that looks at how bimodal delivery systems utilizing drones can impact traffic conditions on the transportation network. This is a joint work with my advisor, Ramtin Pedarsani, as well as Professor Negar Mehr. Online shopping and at-home delivery has become a staple part of our lifestyles since the past decade. As this demand for e-commerce steadily rises, last mile delivery, or the transportation of goods to the receiver happening in the last leg of the trip, becomes an ever more present bottleneck in the supply chain. With consumers relying more on online orders, we see a precipitous increase in delivery truck traffic, impacting travel time, as well as many other factors within densely populated urban areas. Specifically, a case study investigating parcel delivery operations in London shows that as light good vehicle traffic continues to grow, traffic congestion in central London is predicted to rise 60% by 2031. One potential solution to the growing demand experienced by logistics systems is incorporating drones. Due to their aerial reach, drones possess an inherent versatility that makes them promising for last-mile logistics networks. Both Europe and the United States have taken critical steps towards integrating drones into their airspace infrastructure, performing both economical and environmental assessments. We have also seen many recent works provide theoretical contributions to the field by extending well-known combinatorial optimization problems to include drones as well as trucks, namely the traveling salesman problem with the drones and the vehicle routing problem with the drones, as well as variants of these formulations with additional heuristics. Unlike the combinatorial optimization problems mentioned, which focus on minimizing parcel latency, our work also incorporates societal latency, allowing us to focus on the impact drones have on road congestion. To quantify this impact, we propose a bimodal delivery network consisting of delivery trucks, drones, and regular vehicles. We then study the effect stopping trucks have on roads using simulations, specifically looking at how road latency is affected by stopping trucks and constructing a linear model for latency. Using this model, we design an objective function as a trade-off between parcel and societal latency, solving for the socially optimal routing scheme. We pose a scalable optimization framework using a quadratic objective function which acts on our control variable x, the flow of stopping trucks along paths. Using this objective, we perform a case study to show a model on the Swa Falls transportation network. The key idea of our work is that by incorporating both societal cost and parcel latency in our optimization, we can assess the impact drones have on logistic networks from multiple stakeholder perspectives, namely the receiver and sender who are concerned with the parcel and the residents who are concerned with traffic congestion. For the rest of the talk, I will go over the network model used and its formulation. Following this, we will discuss the simulation studies and how latency for varying roads was modeled. And finally, I show the results on our case study. Let's begin with the network model. As I go over this model, I will highlight the corresponding notations we use in our work that describe the model properties. We begin our network model by defining a set of nodes and a set of directional edges connecting the nodes. These two define the road network, which can be thought of as a graph. On this graph, we think of our delivery locations as the nodes themselves, with V0 being the central delivery hub. The paths are predefined for us, and we can also define the sets of uplink and downlink edges for each node. Our job is to find the optimal routing scheme for trucks, which we do by allocating them along the predefined paths. Note that this truck flow must satisfy the demand at each vertex, which we can think of as the sum of demand fulfilled by trucks and drones, respectively. To calculate the actual truck flow along edges, we define a linear transformation of our control variable x, the flow of trucks along paths. And finally, we conserve the flow along the graph by forcing the difference in incoming and outgoing trucks at a node to be equal to that node's truck demand. So far, we have not discussed the latency on the road edges. We note that we can predefine free flow latencies for each edge, And then using our later discussed latency model, we can compute the latency as a function of this free flow latency, as well as stopping truck flow and total flow on the road. We also model stopping trucks along an edge, where we consider that trucks on a path delivering to some destination node will stop along the final edge of that path, as well as all edges departing the destination node. This formulation allows us to keep the flow of stopping trucks linear with respect to our decision variable, while still capturing the notion that trucks will spread their deliveries around the destination node. And finally, we consider the flow of regular cars, or nominal flow, as a constant predefined by the network. All of these components define the road network. And since we want a bimodal delivery system, we extend our network, creating a separate set of nodes and edges. We can think of this as the aerial network, where we note that due to the versatility of drones, we allow them to take direct, though not necessarily straight, paths from the central delivery hub to the destination nodes. We can predefine the latency on these paths. The flow of drones is computed as the leftover parcel flow after routing trucks, and our goal is to compute the latency of all parcel deliveries. And this is a sum of the parcel latencies delivered by trucks and drones. And for the aerial network, we use a predefined latency of our aerial paths. Finally, we have the societal latency, which we can think of as the latency incurred by the nominal vehicles. Remember that we expect our model to capture the effect stopping trucks have on latency. And here, beta is a scaling factor that determines the total flow of nominal cars on the road. And finally, I remind you that the objective is posed as a trade-off between parcel and societal latency, where gamma captures this trade-off. As usual, we want to find the value of our control input that minimizes a given objective function subject to a set of constraints. Our control input is the set of truck flows along the predefined paths. Our objective function is a trade-off between societal latency and parcel latency, where we note that this can be expressed as a quadratic objective. And our flow constraints are imposed to make sure each path has a positive amount of flow, and demand constraints are imposed so that the difference in flows incoming and outgoing at a node is equal to the truck demand at that node. And finally, the cost constraints are imposed to make sure that the system can run under some budget C0. Let's look at the simulation studies. This is what we use to capture the effect stopping trucks have on road capacity and latency. Using Sumo, an open source traffic simulation package designed to handle large networks, we simulate two types of vehicles, cars shown in yellow and stopping trucks shown in red. In the simulation, we control the total inflow of incoming traffic, and as we keep this constant, we increase the ratio of stopping trucks on the road, where we can see them causing congestion. As we expect this effect to vary based on how busy the road is, we also vary the total inflow, simulating increasing amounts of stopping trucks for each inflow level. We repeat this analysis for 3-lane and 4-lane roads, which we designed to have faster moving traffic. Here we point out that unlike the 2-lane road, traffic is able to move freely in the fast lane even when trucks are stopping. Let's look at the effect stopping trucks have on road capacity. Using our simulation, we can observe the results for varying amounts of inflow. Let's first set the number of stopping trucks to practically 0 and observe the regular conditions on the road. We represent the total inflow with a dashed line as it is a constant throughout our simulation, where we first look at when it is at 50% of our capacity. We then look at the output flow of that road, specifically noting that the steady state outflow with a circle, we can see that the road is under capacity as outflow matches inflow. We repeat this, increasing the inflow, seeing that the road is able to maintain outflow until we reach the capacity. Now, let us look at what happens when we add trucks to the 2-lane road. When inflow is small, we see that the road can maintain this flow even when a portion of the traffic is stopping trucks. Now, as we increase the inflow to 50% of the capacity, we see that the road cannot maintain the flow, showing the capacity is effectively decreased as stopping trucks are added. The same is observed if we keep adding inflow. We compute this drop in capacity noting it here at roughly 41%. Finally, we look at the results for multiple lanes, where we note as we move down, we increase the number of lanes. And looking at the effective drop in capacity, we see that 3 and 4 lane roads are less affected by stopping trucks. Looking at specifically at the latency now, we observe how increasing the total flow on the road affects the latency, where we measure it in terms of the free flow latency. We observe that without trucks, all roads follow their free flow latency. Well, of course, as inflow approaches capacity, latency slightly increases above free flow. We note this with the dashed line represents the flow without trucks, and the solid lines represent different lane roads with 10% stopping trucks. As we saw previously, the 2-lane road is highly affected by stopping trucks, while 3 and 4 lane roads better handle stopping trucks. So far, we have observed that stopping trucks have a negative effect on road capacity and latency. And how do we actually model this latency? Well, let's take the 2-lane road, for example. We perform a linear regression over our collected data, and we model latency as a function of the total flow and the portion of stopping truck flow. The color represents latency on the road, where we see that increasing truck flow is the main contributing factor to increasing latency. This is done for all road types, where we observe again that the amount by which stopping truck flow increases latency decreases as we add more lanes to the road. Finally, we are ready to look at the results of our case study. For this, we choose the Swamp Falls Transportation Network, which is a suburban metro area in South Dakota. It contains 24 nodes, and we choose the central hub based on real locations of delivery centers. We use the reported values for best known edge flows and edge capacities, where the edge color represents the nominal vehicle flow as a percentage of that road's capacity. The surrounding downtown area is located here, where we can see it is relatively busy. For each origin-destination pair, we consider the 50 shortest paths and optimize our objective for a demand of 5,000 parcels per hour with a 40,000 hourly budget. First, let's look at the results when there are no drones, which we derive by manipulating our constraints. On the left, we see our depicted solution when we minimize for parcel latency. Here, the edge colors represent the increase in societal latency experienced on the road once trucks are introduced. On the right, we depict our solution when minimizing for societal latency instead. The table lists the numerical results, where we note that there is a disproportional trade-off between parcel and societal latency. When minimizing for societal latency on the right, traffic conditions on the road remain similar. Meanwhile, parcel latency increases by over 50%. This occurs because trucks are rerouted on time-inefficient paths. So what happens when we allow drones? We expect traffic conditions to improve. Looking at our solution for parcel latency on the left, we can see that the downtown area becomes less congested. Note that we use node colors to represent the portion of deliveries done by trucks, which depict that the downtown area is being taken care of by drones. When we instead optimize for societal latency, we reroute drones so that trucks can take roads that least affect societal latency. Looking directly at our table results, we can see that bringing drones into the delivery system allows us to decrease both the parcel and societal latency as compared to our previous table. We also note that in both cases, the proportion of drone to truck deliveries stays the same, which is highlighted by the cost in our table. This is expected since in this setup, drones are generally faster, and hence our solution will utilize as many drones as it can afford before satisfying the rest of demand via trucks. There are many other setups to consider, changing parameters such as speed, cost, and total demand. Our framework lets one do this seamlessly, allowing logistic operators to account for both the parcel delivery time and the effect the routing strategy will have on road congestion. To summarize our contributions, we propose a network model for congestion-aware bimodal delivery systems incorporating drones. We perform simulation studies to capture the effect stopping trucks have both on road capacity and latency, and we constructed a scalable quadratic optimization problem and applied it to the Swamp Falls Transportation Network. We hope our work encourages further research in this topic, as drones can help improve last-mile logistics networks, both by alleviating traffic congestion on the road and decreasing parcel latency. Thank you.